this lesson, we will look at the first derivative test. The first derivative test. What are we doing the test on? We use the first derivative to do a test on the function. In other words, we are going to find the characteristic of a function using its first derivative. Now, what do you know about the first derivative so far? Well, in the last lesson we talked about the maximum, the relative maximum and the relative minimum of a function. When does a function has a relative maximum? At a point where the function has a relative maximum, the first derivative is 0. Similarly, at a point where the function has a relative minimum, the first derivative is 0. Also, we know that there can be points where the function has a sharp turn, where the derivative is undefined. Well, so all these, the first derivative gives you some information about the behavior of the function. Now, look at the two functions that I'm going to write on the board now. X equal to negative 2t, that is one function. And another one is x equal to positive 2t. What is the difference between these two functions? Well, you know that the derivative of the first function is negative 2. The derivative of the second function is positive 2. What is the difference between a negative derivative and a positive derivative? Well, let's have a look at the first function. What does it tell you? X equal to negative 2t. It tells you that when t equal to 0, the object is, well, this gives you the position of an object with time. So, at x equal to 0, the object is at the origin. At x equal to negative 1, oh well, t cannot be negative, so we can only assign positive values to t. As t changes, the x value changes. When t equal to 1, x equal to negative 2, the object is here. At x equal to 2, the object is at negative 4. So, well, this is negative 1, that's negative 2, negative 3, negative 4. So when t equal to 1, the object is at negative 2 meter. At t equal to 2, the object is at negative 4 meter. What is happening to x? X is decreasing. So, if the derivative of a function is negative, it tells you that the function is a decreasing function. On the other hand, if the derivative is positive, look at that. When t equal to 1 in the second function, where is the object? The object is at x equal to 2. When t equal to 2, the object is at x equal to 4 meter. Here you have an increasing function. Very important. So, we actually now have two information what the first derivative provides us. What are they? Well, if the derivative is negative, it tells you that the function is a decreasing function. If the derivative is positive, it tells you that the function is an increasing function. And from the last lesson, we know that corresponding to a critical number, what does a critical number tell you? A critical number is the value of the independent variable where the derivative is either 0 or undefined. So at a critical number or a critical value, the derivative is 0 or undefined. Now, these two combined gives you a lot of information about the function, and that's what we're going to use in this lesson to solve problems. Look at the graph of this function. Now, you can say at x equal to a, suppose this is a, at x equal to a you have a relative maximum, is that right? I'm going to say the relative maximum. At x equal to b you have a relative minimum. And so tell me, what is the behavior of the function from negative infinity to a? So if I say on the interval negative infinity to a, if I draw, say, some broken lines here, I'm talking about the interval from negative infinity to a. What is the behavior of the function? Negative infinity to a, f of x is increasing. Is that right? F of x is increasing. What can you say about the derivative of the function? You can see the derivative is the slope of the tangent line at a given point. If you draw the slope of the tangent line anywhere on this graph, that gives you a positive slope. So you can see on negative infinity to a, anywhere you draw the slope of the graph, it will have a tangent to the graph, it will have a positive slope, telling you that the derivative is positive. So on the interval where the derivative is positive, the function is increasing. And look at a tangent line on the interval from a to b. Suppose this is b. So on the interval a to b, you take any point and draw a tangent line. What can you say about the slope of that tangent line? It is negative. It means the first derivative of this function at any point on the interval a to b is negative. The function therefore is decreasing. And what can you say about the interval from b to infinity? From b to infinity, the first derivative is positive. The function is increasing. You can draw a tangent line anywhere on the graph, it has a positive slope. So the first derivative is positive, therefore the function is increasing. Now, let's put it all together. On the interval negative infinity to a, the first derivative is positive, therefore the function is increasing. On the interval a to b, the first derivative is negative, therefore the function is decreasing. On the interval from b to infinity, the first derivative is positive, therefore the function is increasing. And now, to the left of a, the function is increasing. To the right of a, the function is decreasing. Therefore, the function value at a must be a relative maximum. That is the only alternative. Is that right? If on one side the function is increasing, on the other side is decreasing, it means at that point you have a relative maximum. Similarly, look at the behavior on the left and right of b. On the left of b, the function is decreasing, and on the right it is increasing. That means it decreases, reaches a minimum, and then increases. So the function value at x equal to b, or we call it f of b, f of b is a relative minimum and f of a is a relative maximum. Well, we will now use this concept to describe more in detail of a function, and we can also draw the graph of a function using this information. That's what we're going to do next. Let's now use this information to solve a problem. Look at this problem. Find the critical numbers of f of x equal to x squared plus 8x plus 10, and find the open intervals where f of x is increasing or decreasing, and find all relative extrema. And once you have done that, you also get an idea of what the graph of the function is like. Alright, let's start by doing the critical numbers. What do? Find the derivative of the function. Well, this is our function. Now, what is its derivative? F prime of x equal to, derivative of x squared is 2x, plus derivative of 8x is 8, and that is the derivative. To find the critical numbers, we set the derivative equal to 0, because critical numbers occur where the derivative is either 0 or undefined. Now, there are no x values which will make this undefined. So critical numbers exist when the derivative is 0. So set this equal to 0 and solve for x. What is x equal to in this case? Well, x equal to 2x plus 8 equal to 0 gives you x equal to -4. So x equal to -4 is a critical number. What does that mean? It means you will either get a relative maximum at that point or a relative minimum. Now, what the critical number does is to divide the whole domain of the function into two intervals. Now, the domain of this function is -infinity to +infinity. Now, this critical number divides it into an interval -infinity to -4. Now look at the open interval. The end points are not included. So this is one interval. What is the next interval? The next interval is -4 to infinity. So what the critical number does is to divide the domain of the function into certain intervals. There is only one critical number there, therefore the domain of the function is divided into two intervals. Alright, let's now look at these two intervals, and we need to figure out the behavior of the first derivative. Now remember, you know that if the first derivative is positive, then the function is increasing. If the first derivative is negative, then the function is decreasing. Now, how do we know whether the first derivative is positive or negative on this interval, -infinity to -4? What do? All we need to do is take a number on that interval and set x equal to that number and find the derivative value. And if that is positive, then for all values in this interval, it will be positive. Now we're going to call it the test number. We take a test number. Now remember, a test number can be any number on that interval. Doesn't matter which one you pick. Alright, give me a convenient number on this interval, -infinity to -4. Well, I'm going to call it the test number. The test number. Now, what is the test number we can take on that interval? I think it is -5. Let's take -5 as the test number on that interval. Alright? If you have taken the test number, what is the value of the first derivative at that test number? In other words, what is f prime of -5? What we need to do is set this x equal to -5 to get f prime of 5. Now, can you tell me what that value is? Set x equal to -5. -5 times 2 is -10. -10 plus 8 is -2. So f prime of -5 is -2. What it tells you is that throughout this interval, the first derivative will be negative, because you put any number here on this interval, you will get a negative answer. So on -infinity to -4, the first derivative is negative. So what does that tell you of the behavior of the function? Well, the function therefore is decreasing. That's right. So you can immediately say, therefore f of x is decreasing. All right, let's go to the next interval. -infinity to -4 to infinity. Give me a test number on that interval, a convenient test number. Well, a test number on that interval seems to be 0. 0 is the most convenient one, is that right? 0 is on that interval. All right. Then what is f prime of 0? What is the value of the derivative at that test number? F prime of 0, in other words, go to your first derivative and put that test number in there. That will give you f prime of 0 equal to 8. The first derivative is positive. If on an interval the first derivative is positive, the function is increasing. So we now know that the function is increasing. Now you get a picture of the graph of the function now, isn't it? From -infinity to -4, the function is decreasing. From -4 to infinity, the function is increasing. Therefore, at x equal to -4, what do you think is the behavior of that function? At x equal to -4, you have a relative minimum. And what is that value of the relative minimum? In other words, what is the value of f of -4? Can you do that for me? What is the value of f of -4? When x equal to -4, what is the value of that? Well, you can do that maybe mentally, but I'm going to show it to you on the calculator how you can do that quickly. -4 squared is 16. 8 times -4 is -32. -32 plus 16 is -16. Plus 10 is -6. So f of -4 is -6. That means you can now draw the graph of the function if you want. Is that right? I'm going to do that in a small fashion here. What it tells you is that, well, let me draw that like this. That's x equal to 0, x equal to -1, -2, -3, -4. And how does the function behave? Well, at x equal to -4, I'm going to put a vertical line. Why is that? That is our critical number. And we divided the domain of the function into -infinity to -4 and -4 to infinity. And you know that at x equal to -4, the function value is -6. So it will be -1, -2, -3, -4, -5, -6. Now, This is the point where you get x equal to -4 and the function value is -6. And that is a relative minimum. And we know that from -infinity to -4, f of x is decreasing. So look at the graph of the function. It's decreasing, reaches a minimum at x equal to -4. And from x equal to -4 to infinity, it is increasing. There you go. And there you got the picture of the function graph. You see, the first derivative test. By looking at the first derivative, we understand the behavior of the function. All right? Okay. Let me now show you how to use a TI-83 or TI-84. Well, remember TI-84 and TI-83 have the same key structure. So I'm going to show you how TI-83 can be used to find these values when the functions are rather difficult. All right, what you need to do is go to the graph mode. So press y equal to and put in this function, x squared plus 8x plus 10. So let's do that. X squared plus 8x plus 10 is our function. Now, our next function, y2, is going to be the derivative of y1. So look how I'm going to do that. First of all, access the math menu. Access the math menu and scroll down to number 8, nth derivative. Enter. So function y2 is going to be the first derivative of y1. You need to write y1 there. Now, where do you get y1? Look at it again. Press vars. And there, go to the right and choose y vars, y variables. And it is the y function you need. That's the first one there. And it is selected, so enter. And you see y1, y2, y3, and so on. We want y1, so enter. So we have the nth derivative of y1. Now you got to put a comma there and say x, the derivative of y1 with respect to x. You need to repeat that again, comma x, and close the parenthesis. So you got y1 is the function, y2 is the first derivative of the function. You can now repeat, if you want, y3 as the derivative of y2. We will do that in our next lesson when you talk about the second derivative test. All right. Now, if you graph this, you know how the graph of the function. Let's graph that. And look at that, the graph of the function. And then the graph of its derivative function. Look at that. Now, if you notice here, the derivative is negative. You see, any part of the graph that is below the x-axis is negative. So the derivative is negative from all the way to -infinity to -4. And the derivative is positive all the way from -4 to infinity. And the derivative is 0 at x equal to -4. It means the derivative graph is crossing the x-axis at x equal to -4. All right, let's now go and quit this. Let's evaluate the derivative at what was our first test number we chose? On the interval -infinity to -4, we chose -5. So look at that again. I'm going to go again, vars, press vars, and the right arrow to y vars. And we need the function variable, so enter. and choose y2. All right, we want the value of the derivative at x equal to -5. So put a parenthesis and enter -5 and enter. It gives you the value of the first derivative at x equal to -5 is -2, telling you that the derivative is negative. All right, similarly, once again, was y was function, let's go to y2, and what was the second test number we chose? I think that was 0. y2 of 0 is 8, telling you that it is positive. And then we wanted the function value at the critical number. All right, find the function value at the critical number. Remember, the function is y1. So this time, go to was, y was, function, choose y1. Find the value of y1 at the critical number. Critical number is -4. There you got it, -6. So once you know how to use a calculator, these kind of problems become very simple for you. Okay, let's try another problem. Bear with me for the rolling that the projector is producing. Find the critical numbers of f of x equal to x squared over x squared minus 9. And find the intervals where the function is increasing or decreasing, and locate the relative extrema. Now, where do we start with this? Our starting point is to find the critical numbers. Now, how do we find the critical numbers? We take the function, find its derivative, and set it equal to 0. Critical numbers are the values of x where the derivative is either 0 or undefined. So let's first obtain the critical numbers and by setting the derivative equal to 0. Now, the function is f of x equal to x squared over x squared minus 9. All right, can you do the derivative of this? Well, remember, the derivative of this is denominator times the derivative of the numerator minus numerator times the derivative of the denominator all over the square of the denominator. Now, I wrote that step for you. So that would be denominator times the derivative of the numerator minus numerator times the derivative of the denominator all over the square of the denominator. Well, you know these steps rather easy, so that will be x squared minus 9 times the derivative of x squared is 2x minus x squared times the derivative of x squared minus 9 is again 2x. And the denominator will not change. Alright, can you simplify that? It will be 2x squared, is that right? 2x squared minus 18x minus 2x squared. And the 2x squared minus 2x squared will cancel. The numerator is negative 18x and the denominator is x squared minus 9 all to the power of 2. Well, first we set this equal to 0. Remember, a rational expression becomes 0 when its numerator is 0. And a rational expression becomes undefined when its denominator is 0. Alright, let's use that. We set f prime of x equal to 0, and this becomes 0 when 18x equal to 0. And 18x equal to 0 occurs when x equal to 0. So x equal to 0 is a critical number, and that's a point where the derivative is 0. Well, a critical number can also occur where f prime x is undefined, and f prime x becomes undefined where the denominator is 0. So let's set the denominator equal to 0. X squared minus 9 equal to 0. Well, what are the values of x that makes x squared minus 9 equal to 0? That gives you x equal to positive 3 or negative 3. But if you go back to your function, are x equal to 3 and x equal to negative 3 in the domain of the function? Well, no, because both these values will make the function undefined, and therefore these are not in the domain of the function, and therefore these are not critical numbers. The only critical number is x equal to 0. But now watch my statement carefully. In order to understand the behavior of the function, we cannot ignore these numbers. Although they are not critical numbers, we need to use these numbers in order to study the behavior of the function. Because, at least from your understanding of functions from pre-calculus, you know that these actually numbers represent vertical asymptotes. So, the behavior of the function to the left and right of these numbers need to be known in order to draw the graph of this function. So, when you have the numbers where the derivative is undefined and when they don't belong to the domain of the function, we are going to call them partition numbers. Alright? So, since they are not in the domain of the function, they are not critical numbers, and x equal to 0 is the only critical number. But, as I said earlier, we are not going to throw these numbers away. We are going to use those numbers to divide the domain into 4 intervals. So rather than calling them critical numbers, we'll call them partition numbers. Now, do you understand why we got to use them? Because on the left and right of these numbers, the behavior of the function is very peculiar, and we need to know that. And so we need to use those numbers in order to divide the domain. Now tell me, we got one critical number and 2 partition numbers. So how many intervals are we going to divide the domain into? Alright, look at that again now. We got x equal to negative 3, x equal to 0, and x equal to 3. There are 3 numbers. 1 critical number and 2 partition numbers. Now, I wrote them in the ascending order so that it makes it easier for us to construct the intervals. Alright, what are the intervals we can divide the domain into? We can divide the domain of the function into 4 intervals. What are they? We can divide the domain, well, let's first of all put these numbers down. That is x equal to negative 3. That is x equal to 0. That is x equal to 3. It means we're going to have an interval from negative infinity to negative 3, another interval from negative 3 to 0, another one from 0 to 3, and finally from 3 to positive infinity. So, the first interval is negative infinity to negative 3. Then we have negative 3 to 0. And we have 0 to 3 and 3 to infinity. What is our next task? Well, our aim is to find whether the first derivative is positive or negative on these intervals. If the first derivative is positive, we know the function is increasing. If the first derivative is negative, we know the function is decreasing. So after dividing the domain into these intervals, we take test numbers on these intervals. Alright, can you give me test numbers on this interval? Give me a test number on this interval, negative infinity to negative 3. Well, negative 4 is a good choice. Give me a test number on negative 3 to 0. Negative 2 is a good choice. You can choose any number. Well, negative 2.9, negative 0.01, all those are possible. But negative 2 is a more convenient number. Alright, a test number in the next interval, 0 to 3, is 2. And on the last interval, from 3 to infinity, the test number is 4. Alright, why did we choose these test numbers? So that these numbers can now be put in the expression for the derivative. Our aim is to find whether the derivative is positive or negative on these intervals. Therefore, we are looking for the sign of f prime x. Is f prime x positive or negative? Alright, shall we use the calculator one more time to do that? Okay, let's use the calculator to find the sign of the derivative at those test numbers. What do? First we go to y equal to, well, turn on the calculator first. Go to y equal to and enter our function first. Now clear y1 and enter your function. What is our function? F of x equal to, I forgot the function, I need to look at the function. Well, our function is f of x equal to x squared, so that will be x squared divided by, now use a parenthesis now, x squared minus 9. There we go. That's our function. And the beauty of this is, once you have entered your y2 as the derivative of y1 with respect to x, you can leave it there because that is applicable to all functions. Now, we have finished, so if you want to look at the graph, actually you can go and have a look at the graph, but let's do that later on. Let's quit this. Now, what do you want to find? We want to find the derivative of the value of the derivative at our first test number. What is the first test number? Our first test number is negative 4. So we want to find the value, the sign of the derivative at x equal to negative 4. How do you do that? Go to vars, y-vars, function. Now come down to y2 and enter. We want to find y2 is our derivative. We want to find the value of the derivative at x equal to negative 4, and that is positive, right? So that will be, the derivative is 1.46. We are not interested in the value. We are interested in whether the derivative is positive or negative. So at x equal to negative 4, the derivative is positive. Let's go and find on the next test number is negative 2. So let's repeat it. Vars, y-vars, function, come down to y2 of negative 2. And that's also positive. So the first derivative is positive at x equal to negative 4. It's positive at x equal to negative 2. We will talk about that when we finish this. All right. Now our next number is y equal to 2. And I think we can manage it on the screen without going back on the... So if you press second enter, you notice that the earlier entry is brought back. And if you scroll back into it and take off that negative, delete that negative, now you got y2 of 2, and that is negative. There you go. And finally, we got to find y2 of 4. Again, what all we need to do is go second enter, and scroll back onto that 2 and change it into a 4. And that again is negative. So what you notice is, let's go back to the board now. So what do we have? We have the sign of f prime x. This is our f prime x. And at x equal to -4, we found it is positive, greater than 0. And at x equal to -2, also it is positive. So f prime of -4 is greater than 0. F prime of -2 also is greater than 0. How about f prime of 2? It is negative. And f prime of 4 is also negative. Now what that tells you is that on the interval -∞ to -3, the function is increasing. Well, and from -3 to 0 also the function is increasing. But what happens at x equal to -3? It is not in the domain of the function. It is a vertical asymptote. And that's why we need this. Well, on the left of the asymptote, the function is increasing. And on the right also, the function is increasing. So, what do you think how the graph is behaving? All right, let's go there. The function, the derivative is negative on the interval 0 to 3. Therefore, the function is decreasing. And similarly, from 3 to infinity, the function is decreasing. So we find the behavior of the function is increases, decreases, and decreases. All right, let's take these information to the next screen and see whether we can use them to plot the graph of the function. And how about the value of the function at the critical value, f of 0? If you look at the function, what is our function again? Do you remember it? It is x squared over x squared minus 9. What is the value of that function at x equal to 0? X equal to 0 is the critical value. Since the numerator is simply x squared, its value at x equal to 0 is 0. So f of 0 is 0. Or you can go to your calculator and find y1 of 0. You get it equal to 0. All right, let's take this information. Now tell me, the value f of 0 equal to 0, is that a relative minimum or a relative maximum? On the left of 0, the function is increasing. On the right of 0, the function is decreasing. Therefore, at x equal to 0, you have a relative maximum. So that's a lot of information you have about that graph. Now, I have put those down in here. From -∞ to -3, the function increases. -3 to 0, it is increasing again. At x equal to 0, the value of the function is 0. And that is a relative maximum. It decreases and then it decreases. And tell me, what is x equal to -3 corresponds to? X equal to -3 is a vertical asymptote. Similarly, x equal to 3 is a vertical asymptote. Can you use this information to draw the graph of this function? Well, we know that from -∞ to -3, the function is increasing. and from -3 to 0 again, it is increasing. Alright, 0 to 3, it is decreasing. And from 3 to infinity, it is decreasing. Now, one of the clues that you can keep in most cases, if on the left of the vertical asymptote the function goes to positive infinity, on the right side it will come from negative infinity. You see, on the left it is increasing, so it goes like this to positive infinity. So on the right it must come back from negative infinity and increase. See that? Alright, so the function is increasing from negative infinity to -3. It goes to positive infinity there, to the left of -3. And that means it must appear on the right of -3 from negative infinity. There, it increases. And how about on the right? From 0 to 3, it is decreasing. There you go. It is decreasing. Now, it is decreasing and goes to negative infinity. That means on the other side, it must come from positive infinity and decreasing. Now, how beautiful that is. You see? You don't have to really go to a calculator to draw the graph. The first derivative test, the information from the first derivative helps you to plot the graph of the function. Isn't that beautiful? Okay, now try that on the calculator. You have the function on the calculator already, and try and graph it on the calculator. To do this on the calculator, you got to first set the window. So go to the window, and I have set it already. X equal to -5 to 5, y to -10 to 10, and press graph. And look at the way the graph is being constructed. And what's the derivative graph? Well, from negative infinity to 0, the derivative is negative. No, the derivative is positive, and then here the derivative is negative. Look at the graphs of those. Now here you have the graph of the function and its derivative. All right. Okay, I want you to practice this one more time by doing this. Find the critical numbers of f of x equal to x cubed minus 6x squared plus 15. And find the open intervals where the function is increasing or decreasing, locate all the relative extrema, and draw a possible graph of the function. I've given you the critical numbers, and I've also given you the intervals where the function increases, decreases, and so on. And try and do this on your own. Let's try another one, a very good function. A trigonometric function. Very often, most of you have trouble with trigonometry because you don't remember your identities, you don't remember the trigonometric values, but those are very important information. So let's try this. Find the critical numbers of f of x equal to sine x cos x on the interval 0 to 2 pi. Well, remember, the domain of sine x cos x is negative infinity to positive infinity. So to study the behavior, we restrict the interval from 0 to infinity. That makes it easier for us. And locate where the function is increasing or decreasing, and locate the relative extrema. Okay, tell me, where do we start? We take the function, find its derivative, right? Yes. And set the derivative equal to 0 for critical numbers. Shall we do that? Well, our function is f of x equal to sine x cos x. And we have a couple of tasks here. What are they? First, find the derivative of this, and then set the derivative equal to 0 and solve for the values of x to get the critical numbers. And the critical numbers need to be obtained on what interval? We need to get the critical numbers on 0 to 2 pi. Now, first of all, help me find the derivative of this. F prime of x equal to, first function is sine x times the derivative of the second function. Derivative of cos x is negative sine x, plus the second function, that is cos x, times the derivative of the second function. Derivative of sine x is cos x. So this comes out to be, look at this, sine x times negative sine x is negative sine squared x. Cos x times cos x is cos squared x. And that I can write as cos squared x minus sine squared x. Well, you know from solving trigonometric equations, you cannot solve a trigonometric equation if you leave the equation in terms of two ratios. You must bring it down to a single ratio. Can you recall a trigonometric identity that involves cos squared x minus sine squared x? Well, if you go back and look at your identities, cos of 2x has actually three different types. Cos of 2x is 2 cos squared x minus 1. Is that right? Cos of 2x has three different forms, and one of them is 2 cos squared x minus 1, and that is cos of 2x. Another one is 1 minus 2 sine squared x. That also is cos of 2x. And the most important one that we're going to use here is cos of 2x is cos squared x minus sine squared x. So cos squared x minus sine squared x, what we have here, is cos of 2x. So what we're going to do is replace our cos squared x minus sine squared x as equal to cos of 2x. So our derivative function is cos of 2x. And we're going to set this equal to 0. Cos of 2x equal to 0. What are the values of x where cos of 2x equal to 0? Now, there is a little complexity here that I want you to pay close attention to. We want to find the values of x, or the behavior of the function, from 0 to 2 pi. That means we are looking for critical numbers in the interval 0 to 2 pi. But cos of 2x equals 0, you need to solve for 2x. We are not solving for x from this equation. You see, cos theta equal to 0. That theta is 2x. If you want to find x values in 0 to 2 pi, you must find 2x values in 0 to 4 pi interval. I want you to understand that carefully. Remember, we want to find x values in the interval 0 to 2 pi. But this equation allows us to solve only for 2x. That means the values of 2x need to be then found in the interval 0 to 4 pi. Alright, what are the values of x from 0 to 2 pi? For that you need to know cos of what equal to 0? Well, You know that cos of 0 is 1, is that right? Cos of 0 is 1, cos of pi by 6 is root 3 over 2, cos of pi by 4 is root 2 over 2, cos of pi by 3 is 1/2, cos of pi by 2 is 0. So, one value of 2x, we are going to write the values of 2x on this interval. The first value of 2x, so I'm going to say 2x equal to, when 2x equal to pi by 2, cos of pi by 2 will be 0. So one value of 2x is pi by 2. What is the other value? The next one where you get cos value is 0. It is 3 pi by 4. Isn't it? That's right. Now, you got pi by 2, 3 pi by 2, but we got to go all the way to 4 pi. Now, the next value where the cosine will be 0 will be 5 pi by 2. There you go. And where is the next one? 7 pi by 2. Well, 8 pi by 2 is 4 pi. That means in the interval 0 to 4 pi, you get cos of pi by 2 is 0, cos of 3 pi by 2, not 3 pi by 4. Cos of 3 pi by 2 is 0, cos of 5 pi by 2 is 0, cos of 7 pi by 2 is 0. That means the values of 2x on the interval 0 to 4 pi are these. Alright, let me take down these and write those values of 2x. I hope you understood what I'm saying. Well, this is actually done in a trigonometry class. So what are the values of 2x on the interval 0 to 4 pi? 2x equal to, the first value is pi by 2, the second value is 3 pi by 2, the third value is 5 pi by 2, and the fourth value is 7 pi by 2. Now, let me illustrate that again. You can see cos of 0 is 0. Cos of pi by... Did I say something wrong? Cos of 0 is 1. Cos of pi by 2 is 0. Cos of pi is -1. Cos of 3 pi by 2 is 0. And now that is, we have done 0 to 2 pi. That means we got to go one more. Well, 3 pi by 2 and 5 pi by 2. And we are back to 4 pi now. So from 0 to 4 pi, cos of pi by 2 is 0, cos of 3 pi by 2 is 0, cos of 5 pi by 2 is 0, cos of 7 pi, I had messed up over here, so check that again. Cos of pi by 2 is 0, cos of 3 pi by 2 is 0, cos of 5 pi by 2 is 0, cos of 7 pi by 2 is 0. Okay, now these are the values of 2x. Therefore, what are the values of x? The values of x, therefore, are, if 2x is pi by 2, then x is pi by 4. If 2x is 3 pi by 2, then x is 3 pi by 4. If 2x is 5 pi by 2, then x is 5 pi by 4. If 2x is 7 pi by 2, then x is 7 pi by 4. Look at that. These are the critical numbers of x from 0 to 2 pi. I want you to go through this one more time and learn this concept. So you got now the critical numbers, x equal to pi by 4, 3 pi by 4, 5 pi by 4, and 7 pi by 4. Okay, so now x equal to pi by 4, 3 pi by 4, 5 pi by 4, and 7 pi by 4 are the critical numbers on the interval from 0 to 2 pi. Now tell me, how many intervals are there on that interval using the critical numbers? We have the first interval from 0 to pi by 4. The second interval from pi by 4 to 3 pi by 4. The third interval from 3 pi by 4 to 5 pi by 4. And then from 5 pi by 4 to 7 pi by 4. And 7 pi by 4 to 2 pi. There are 5 intervals. So these numbers divide the intervals 0 to 2 pi into 5 intervals. Let's write down those. Let's first write the critical numbers. X equal to pi by 4 is the first critical number. X equal to 3 pi by 4 is the next critical number. X equal to 5 pi by 4 is the third critical number. X equal to 7 pi by 4 is the next critical number. Well, I'm just going to go out of the screen, I think. And so what are the intervals in here? One more time. The first interval is from 0 to pi by 4. The second interval is from pi by 4 to 3 pi by 4. The third interval is 3 pi by 4 to 5 pi by 4. 5 pi by 4 to 7 pi by 4. And 7 pi by 4 to 2 pi. And now we need to take a test number on each of these intervals. Because what's our aim? Our aim is to find the sign of the derivative. Is the derivative positive or negative? And in order to do that, we take a test number on each of these intervals. Alright, give me a test number from 0 to pi by 4. Now, the clue here is, I know most of you can think in degrees better than in radian. Pi by 4 is 45 degrees. Therefore, something from 0 to 45, a convenient number, is 30 degrees. And 30 degrees is pi by 6. So, pi by 6 will be a good test number here. Okay, in that case, give me a test number here. Pi by 4 to 3 pi by 4. What will be a good test number there? That will be, I think, pi by 2. Is that right? Yeah, because 3 pi by 4 is greater than pi by 2. So pi by 2 is a good number there. Now how about 3 pi by 4 to 5 pi by 4? Alright, let's do that. Take a test number here. I took pi by 8 in here. It doesn't matter since you're going to use the calculator. Pi by 6 is a more convenient number if you don't use the calculator. But pi by 8 is actually on that interval. Pi by 2 is on the interval pi by 4 to 3 pi by 4. And pi is a number between 3 pi by 4 to 5 pi by 4. Pi is a very convenient number. How about on the interval 5 pi by 4 to 7 pi by 4? If you keep that 2 circles that I drew earlier, that will help you to figure out this. You see, 5 pi by 4, 5 pi by 4 is actually after completing one circle, you have gone a quarter. That is 5 pi by 4. To 7 pi by 4. What's that number? It will be 3 pi by 2. That's right. Now, and you can choose 11 pi by 3 on 7 pi by 4 to 2 pi. 11 pi by 3 is actually 330 degrees. 2 pi is 360 degrees. So think in degrees, which will actually help you. So we have now the test numbers, and we need to find the sign of the derivative at each of these. Tell me, what is our derivative function? Our derivative function is cos squared x minus sine squared x. But you don't need to worry about it. You know how to deal with on the calculator. So I'm going to show you one more time on the calculator how this is done so that you can fill in these values right away. So our next task is fill in the values of the derivative at these test numbers. Okay, let's do it on the calculator. To begin with, we go to the y equal to and enter our function. Always turn on the calculator first and clear that if you want. Go to the y equal to and clear y1. Don't clear y2. Leave it like that because that's something that's going to stay there. What's our function? And most important, first of all, you need to go to the mode and make sure that your calculator is on radian mode, not degree mode. So bring it down to radian and enter. Very important. The calculator needs to be set on radian mode, not degree mode. And now quit that. All right, let's go to y equal to and write down the function. What's the function that we have? Sin x times cos x. Is that right? So we say sin x times cos x. That is our function. Y equal to sin x times cos x. That's our y1. y2 is the derivative of this function with respect to x. All right, let's quit this and clear the home screen. What do we want to find? If you look at the board, we want to find what is the value of the derivative at x equal to pi by 8. So what do? Find the value of y2 at x equal to pi by 8. So we go to, what do we go to? We go to vars and write y vars and function, that's enter. We want to choose y2 and y2 of what? Pi by 8. So parenthesis pi, do we got pi there? No, I think I didn't get that right, did I? Now we got second caret gives me pi, so pi divided by 8. y2 of pi by 8, and what does that give you? 0.707. All right, take note of these values. We will now continue locating this. Now we need y2 of pi by 2. The second value is pi by 2. All right, let's do that. Second enter brings back that. And what all you need to do is go back and change it to pi by 2 and enter. So you got the derivative at pi by 8 is positive. The derivative at pi by 2 is negative. Next we need to find that at pi. So again go to second enter. And what do? Change that pi by 2 to a pi. In other words, delete, divide by 2. And you notice that I don't need the last parenthesis. The calculator doesn't mind it. So the derivative at x equal to pi is positive. And next, second enter, we want 3 pi by 2. So you got to have now write down 3 pi by 2. Did I get it right? No, I don't have my glasses, so I'm making mistakes. y2 of 3 pi by 2 is negative. And finally, y2 of 11 pi by 3. Let's say, second entry, go back and change that to 11 pi by 3. There you go. y2 of 11 pi by 3 is negative. Now, have you taken down all these? Let's transfer all these to the board. Now, as I said to you earlier, we don't need the values of the derivative at these. We only want the sign of the derivative. We want to know whether the derivative is positive or negative. And we already know that. Well, we found the derivative is positive on this interval, negative on this interval, positive there, negative there, and positive there. Okay. Now, therefore tell me, at x equal to pi by 4, do you have a relative maximum or a relative minimum? F of x. But before we come to that, let's talk about the behavior of the function. What does the function do? What does the function do on this interval? The function, because the derivative is positive, the function is increasing. So the function increases from 0 to 4 pi. How about from pi by 0 to pi by 4? How about from pi by 4 to 3 pi by 4? Derivative is negative, the function decreases. And I'm actually also constructing the graph along with the watch that. The function is increasing from 0 to pi by 4. And from pi by 4 to 3 pi by 4, the function decreases. Look at the graph, it's coming down. Now, from 3 pi by 4 to 5 pi by 4, the derivative is positive. You can see there the function is decreasing all the way. Here the derivative is positive, therefore the function increases, and you can see it increases all the way from 3 pi by 4 to 5 pi by 4. And from 5 pi by 4 to 7 pi by 4, the derivative is negative, means the function is decreasing. It means it must come like this. There you go. And finally, from 7 pi by 4 to 2 pi, the derivative is positive, the function increases. There you go. Isn't that beautiful? It really gives you a complete picture of what the function graph is all about. Now, x equal to pi by 4 is a relative maximum, is that right? On the left the function increases, on the right it decreases. Relative maximum. You have a relative minimum, a relative maximum, is that right? And a relative minimum. The first derivative test, the values of the first derivative actually tells you how the function behaves. All right. And I've actually drawn the graph of that, and you can do that on your calculator right away. Shall we do that? Well, all right, let's graph the function graph. There are two things to do. First is go to y equal to, again turn on the calculator, go to y equal to, and since we are interested only in the graph of the function, disable y2. How do you disable y2? Just bring down your cursor, go to that equal to, let the cursor be on the equal to and enter, and you notice that equal to is no longer selected. That means y2 will not be graphed. All right, now go to window and set the window. What's the window that we are using? We got to draw the graph from 0 to 2 pi. Is that right? So 0, enter, 2 pi, enter. That will be 0 to 2 pi. And Well, y minimum, let's say negative 1.5 to positive 1.5. Will that be okay? Let's graph it. There you go. That's the graph that we just constructed. Is that right? All right. I think you are now ready to do more of these kind of problems on your own. All right, if that is the case, do this on your own. Find the critical numbers of f of x equal to cos x over 1 plus sine squared x on the interval 0 to 2 pi. And determine the open interval where the function is increasing, decreasing. Determine the critical numbers and do a rough sketch of the graph of f of x. Okay.